Hi, welcome. We are Paola and Nicolás.
Today we're going to go over a few operational amplifiers, which are settings which let you do different operations depending on how you place the resistors with only this little component. Next is a non-inverting setting. In this one, we will have, for example, if we get an input signal, we won't have it inverted, but we do have to take into account other things, like the values of the resistors. So from the concept of virtual cut, we know that the signal of the input will be the same signal that is present in this node that we're calling Vx. So we know that Vx is equal to the signal, the input signal. And ideally, since the amplifier does not take up any current, R1 and R2 should be in a series setting. So we know that the current going through R1 is equal to the current going through R2. This, we can rewrite it into the voltages we already know and take out this formula, which after a series of calculations turns out to be this. This little fraction right here is equal to the gain. But we can, and we will be expressing it as the output voltage divided by the input voltage, which is exactly the same thing as a gain, but this is just for more comprehensive purposes. So say we wanted to amplify a sine wave by 5. We would have to make this fraction equal to 4 because this fraction will be added 1. So, for example, we could make R2 be 4K and then R1 be 1K. So it would give us a fraction that equals to 4, plus this one, we would have an amplification of 5. So we have a sine wave, there is, for example, something like this. If we amplify it, we are not going to get inverted like in the last setting, but we are still going to have it something like this.
So here we've got the exact same circuit I was just showing you on the board, but it is on a program that will help us simulate what I attempted to draw for you, the sine wave that is amplified by 5. So a little mid-video reminder that you should always pay attention to your supply voltage. For example, here I am going to be amplifying a sine wave of amplitude of 1 and transform it into one that has an amplitude of 5. So I need to make sure that the supply voltage I'm giving the amplifier is within the range of the input and the output signal. So in this case, since I'm predicting the wave will be of an amplitude of 5 volts, then 15 is good. And for this exact model that I'm using, 15 is usually the recommended number. So anyway, here is the AC source that I was talking to you about that will give us the sine wave. Here it is in an amplitude of 1 volt. And here we've got the setup of resistors that I was just showing you. 4K on this resistor and then 1K in here. These little things that you're seeing on the screen, these are really just connections that I'm able to make wirelessly, let's say. So anyway, if we run this and we check on the tool, the oscilloscope, we are going to see 2 different sine waves. That's because I connected the B channel to the original sine wave and then the A channel to the output signal. So you could see some of the change, so you could see the same thing that I drew on the board, but simulated and made be more in a more accurate shape. So here we've got the red wave, which is the output of the signal, and the green wave is the input. So we place these on the minimum and maximum of each wave. We'll be able to see down here in the numbers of channel A and channel B, that channel B now has a gain of 5 because we started with a sine wave of 1 volt, well, almost 1 volt, and now we're ending up with one that is 5 volts. So yeah.
Now we have the subtractor setting. So in this setting, you have to know that we're gonna have this formula. We're gonna have the resistor 2 divided by the resistor 1. And this is gonna be amplifying the differences between the both of the signals. So we're gonna have B input 1 that is coming to the positive side of the amplifier, and it's gonna be minus the B input 2 that's gonna be the negative amplifier. So less words. This is gonna make the difference between them and amplifier by what we put in the different resistors. But if we only want the differences, we can put all the resistors the same weight. 1K, 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 and we're gonna have like B output is gonna be B11 minus B1 B input 2. Something important that you must know that these two resistors, the one that is in the loop and the one who is in the ground, are gonna be the same, and these two are gonna be the same too. So for now, we have an op-amp here. We know that op-amp is an integrated circuit that can amplify some signals and make different kind of operation between them. So in this case, we have the subtractor setting, and we want to make 5 minus 4. We have two DC volts here, and we want to make a new signal that is gonna be 1 volt. So we're gonna confirm that with the simulation in multisim, and we're gonna see the red wire is the result of the minus, and the orange wire is the 4 volt that we want to compare with. So we get that we have 1 volt and 4 volt as we know. Thank you. Welcome back. We have to change the room, but we're okay. We're gonna do. This is the wave alert inversor, and it works like inverter. There is no change. We have this same equation, but we're gonna add 3 different signals: B input 1, B input 2, B input 3, and we're gonna get this equation here that we can use. The things here is like every signal is gonna have its own resistor, and this resistor is gonna work for all the 3 signals. So we're gonna play with that. I mean, if we want like just have the add of the 3 signals, plus times a minus, we can make all the resistors have the same value. So if all are 1K, for example, we are gonna have a minus the minus, but not this, just the adding of the signals, not the resistor. If you want to make like an average of the course or something like that, we can make the resistor divided by this nth resistor to make the weight. Like in the first cut of the semester, we have like this 30%. We can make 1 divided by 3.333, and this is gonna give us 0.3 that we're gonna times with the value of the signal. Like if I have 5 in the first cut, we're gonna put 5 volts, and things like that. We're gonna add it, and that is. We can make this with all the resistors. So we have 1K acá, 1K here, and 3.333 here, and things like that. Thank you.
So this setting will give you an average signal of the inputs that you've given. And in contrast to the last setting, you could actually give percentages to each signal, whichever you wanted, and it was sort of easy. But here, this is a more complicated circuit, where if you make any of these resistors a different value, you will end up with a very long equation that we do not want to solve. So, for convenience, we will make all these resistors the same. So, with this, we will have a fraction of the 2 resistors and added 1 times the average of all these signals we've got here. To make sure this works, you need to make all these resistors the same value. So, here we've got the average of these, which would be the sum of these divided by the number of signals that we've got here. To customize the gain you want this amplifier to have, you need to take into account that besides only the fraction of the resistors, you also need to add 1 unit. So say you wanted a gain of 6. You would need to make sure that this fraction equals 5, so you'll leave room for 1 unit to be added. So, and this is important, when you assign values to the resistors, you always need to make sure that you add them in kilo ohms or more. This is really a technical condition, doesn't really result in anything equation-wise, but it is something you should take into account if you're going to assemble this in your life. So we should make sure that this fraction equals 5, so we can make this one be 5 kilo ohms, and this one 1 kilo ohm. And in this way we get 5 plus 1 equals a gain of 6.
So for these two, we're doing them both in the same simulation. So you can see the differences between each setting and what they can do. So let's start with the one that is inverting our signal. I believe my partner told you about an example where you could calculate your grade of the semester, and obviously 12 is not a grade you can get. So, well, at least not in this system. 12 is not a grade you can get. So let's input some real values. Actually, I'm going to put one. So we'll put some values that I actually know would give us the result I want. So let's say 3.3 and 2.6. And then 3.6. I know these 3 values will give us an answer that's like, no, that is exactly 3.2. And you may have noticed that we switched the tools of to measure our output, and that's because since we're not using a cosine or sine wave, we only need to see one number. We've switched to a voltmeter, which will tell us, what we need to know instead of showing us a graph. So 3.2, and there we've got the negative sign that comes from us using this type of setting. And then over here, for the non-inverting setting, we've got a little bit of a dilemma. In the board, you may have seen that that you had these two resistors, but if you put any value to these resistors, you won't get the average, but you will get the sum of the two values that you put in. So say we got 10 volts and 5 volts. Oh, actually, this is too close to the limit. So we should change it so we can actually know if this is going to go wrong. So here I'm changing the supply voltage to be a higher value because the result we're expecting to get is actually 15, and we want to make sure that the output signals has some room to be nearer or farther away from the supply voltage. 20 is still an acceptable number, it's just not the most recommended one. For this amplifier, the maximum I believe is 22, so with 20 we're actually still fine. So let's run this, and there we have 15. So what if we actually wanted to use this to average both of these numbers? Then we would have to look at the equation and realize that the amplification these signals would have would be 1 plus the fraction of these two. So if we want this average to be multiplied only by 1, we have to get rid of one of these. Preferably, let's see. Well, let's get rid of this one. Oh, hold on. Let's get rid of this one. We still have to trace the little loop here, so it's gonna work. But we've disappeared that. There we go. And now we should get the average between these two signals, which is 7.5. And there we go. We can actually use these settings to get an average of two signals and to add two signals.